control. Okay, last class we discussed that automatic flare control system. Okay, then why we need automatic flare control system, all those things. Today we will discuss a glide slope coupler along with your automatic flare control systems. Okay, so the ultimate goal for both the military as well as commercial aviation is must be the aircraft should be operated in all weather operations. Then how can it is possible to operate the aircraft in all weather operation? Means without a visual reference of runway, the pilot can be able to land, or we can able to land the aircrafts. Okay, so if you want to achieve this, you must accomplished by a automatic landing system. It will guide the aircraft down a predetermined glide slope, and then I come to pre-selected altitude, then it will go for a flare path, then it will comes to landing to touch the touchdown points. Therefore, so from up to approach path to your descent to were landing fully automatic. Then we made with, because some bad weather condition, the pilot cannot see the visual reference of runway. So this will be engaged with your automatic landing systems. So the automatic landing systems we are used in the Chennai airport is to be a ILS, instrument based landing system. Okay, this has a three main components. One is marker beacon, then is a glide slope coupler. That glide slope will be located in the end of the runway. It will guide the aircraft to the vertical reference. It will give the vertical reference to the aircrafts, because there is a glide slope receiver that will be located in your aircraft. It will be guide your aircraft to your pre-selected altitude that will comes to. Then your localizer will be helpful to align your aircraft with your center line. The marker beacon will be indicates whether how much distance far away from the airport. There will be, once the aircraft comes to nearby the aircraft, each marker beacon. Suppose if we are so far from 14 nautical mile from this airport, then maybe the outer marker beacon will be blink on. Now we will comes to very close to this aircraft. That based on that there will be light indication. It gives to the pilot. So we are in the, so far from the airport from some nautical mile. So that information will be provided by your marker beacons. So this here the entire things we can in this section we will cover the longitudinal control portion of your such a systems. So this section we are going to address the design of glide slope coupler and automatic control system and altitude control altitude hold control system. All these one thing is common to control your flight path angles. So this automatic control of the flight path angle without simultaneous control of airspeed. So without controlling the airspeed, it is not possible to control your flight path angle. Whether you have to control the speed either manually or automatically. Okay. So if you design a coupler, if you come design your automatic landing system, you must concentrate on your velocity control of your aircraft. Whether you have to control the whether we have to provide velocity control through manual or through automatic systems. Okay, but you must control the airspeed of the aircraft. Okay, so this portion will today we are going to cover to discuss that is your glide slope. First we think is we take one basic autopilot system with that with velocity rate feedback. Then we discuss what is the need of a speed controller in this design of glide slope coupler. After that we couple with your glide slope coupler. Then we have to discuss your automatic flare control system also. So this is a longitudinal equation of motions. So this equation motion we already studied in aircraft stability and control. So we need to go for how we are getting that. We simply take that equations only. Okay. So this equation will be relate all these parameters. Okay. Where alpha is to be your angle of attack, theta is to be your pitch angle, then del E, that is elevator deflection angle. So this equation of motion will be gives your longitudinal equation of motions for these various design parameters. So now we take your basic autopilot of the jet transport aircraft. The landing configuration where the aircraft flies at a sea level is 200 feet per seconds. This is an assumption we made here. So these were basic autopilot for the jet transport aircraft. These landing configurations. So one is to be your is elevator transfer function. These to be very aircraft transfer functions. These aircraft transfer function, how we can obtain, we come from these equations. These equations, or this, if you take any of these two equation, this equation where del G is your input, where theta of S is to be your output. Okay, then we need to find out your the ratio of output is your pitch angle, input is your elevator deflection angle. So we get the aircraft transfer function. This were aircraft transfer function for longitudinal equation of motion. That is, it is called as a elevator transfer function. Elevator transfer function. Elevator transfer function. So in this case, we will put the velocity rate feedback. So we will discuss what is the essential for your velocity rate feedbacks. Okay, that is your, it is called as your rate gyrosensity. This S is called as your rate gyrosensity. Rate gyrosensity. Then it is a theta dot S. If you put integral, then we will get theta. Then it will come reference to your reference pitch angle. Whether you have aircraft, you decide where reference pitch angle or not. Suppose if the aircraft flies a certain altitude with a desired pitch angle. Okay, suppose if there is any gust or it will encounter, maybe the pitch angle will be deviated. That will be sensed by this. This is your basic autopilot for jet transport. So it will automatically sense your, then based on that it will initiate your voltage signal produced by the amplifier, that will initiate your elevator deflection. So this elevator, based on this, the elevator will be deflected, then we will get a desired pitch angle. Okay. So today we try to sketch the root locus for your inner loop of your basic autopilot landing configuration system. This is your inner loop. This is your outer loop. Well, sketch the root locus for inner loop as well as outer loop of basic autopilot for jet and transport aircraft. Then we came to know that what is the essential for your rate gyrosensity. Why we incorporate velocity rate feedback. Then after that we try to sketch the response of the system with rate feedback without feedback. Okay. Now these were inner loop having a transfer functions. One is elevator transfer function. So I take only the inner loop. So this inner loop is elevator transfer function. It is called as a minus 10 divided by S plus 10. Where aircraft having a transfer function is minus 1.2 S plus 0.585 divided by S square plus 1.5 S plus 1.47. From that I get theta dot rate feedback is given to here. This is the rate gyro sensitivity. Here we put rate gyro sensitivity as a feedback. That means we put symbol k instead of s, because here we is using the transfer function times s. Therefore, we need to avoid this confusion. I make it as a k symbol for your rate gyro sensitivity. Okay. So we try to sketch the root locus for your inner loop. Okay. So here input is elevated deflection angle. Here it is a theta dot pitch rate. Okay. Then if we cut this one, it will comes to open loop transfer function. Therefore, your open loop transfer function g of s into your h of s minus 10 into minus 1.2, we will get 12 into s plus 0.585, then we will get s square plus 1.5s plus 1.47 into a feedback is to a rate gyro sensitive value. Therefore, initially we make it as a rate gyro sensitive value. Then we try to sketch the root locus for this following transfer function. Okay. We try to sketch the root locus for this following transfer function. Okay. So how can you sketch that? We please locate your poles and zeros of your given open transfer function. I have one poles that is called as a 0.1 zeros, that will s equal to minus 0.585. Then our two poles, one is s, while solving this equation, s square plus 1.5s plus 1.47 equal to 0. From that we will get poles of your given open loop transfer function. Okay. And okay. Then how can you write the code for this one in MATLAB? Simply we write because we already solved so many problems of how to sketch a root locus. So we try to sketch this root locus by using MATLAB. So here it is your, we need to define your transfer function. This is your loop transfer functions. Okay, that is called as your numerator. So I'll use this. For your numerator is equal to, what is your numerator transfer function? The coefficient of s is 1. Use open bracket 1. Then the constant term is 0.585. Then your denominator is equal to, this is, and also we will get s plus 10. Yes, this is a multiplication. These two blocks is a cascade block. Minus 10 into minus 1.2. We will get 12 into s plus 0.585, then s plus 10 into s square plus 1.5s plus 1.47. Therefore, this your denominator is a combination of two functions. Here, this function as well as this function. Therefore, it is two functions. Therefore, use a common convolution of two functions. CONV convolution of this bracket. Then first you define one function, that is called as a s plus 10. The coefficient is 1 comma 10 comma, next the coefficient is s square is 1 space 1.5, then space 1.47. then you close this project. Okay, then your transfer for G, if you define G is equal to your transfer function. Here also the multiple of 12, therefore use 12 times 12 star transfer function TF of your numerator comma denominator. Therefore now I will get this entire save function, the transfer function. Then we need to sketch the root locus. So use the command rlocus, rlocus of your G, rlocus of G. Okay, use this command. You try to sketch the root locus by using MATLAB. Or otherwise, if you want to sketch the theoretically means you please locate your poles and zeros. So one pole is located S equal to 1 zeros, S equal to minus 0.585. The zeros are marked as a cross symbol, sorry, small circle. This called as S equal to minus 0.45. Then while solving this equation, then another one pole is located at S equal to minus 10. Here one pole is located at S equal to minus 10. Then while solving this equation, S square plus 1.5 S plus 1.47, then we will get the poles. If we solve this equation, then we will get some poles. Then we will look at the poles. Maybe it's a complex conjugate poles. Then we try to sketch the root locus. Okay, next step is we have to verify whether the root locus lies in the real axis or not. Then we take some test point. The right hand side, the test point total number of poles and zeros lies in the test point is R number. Then the portion will be part of the root locus. Then we need to check breakaway and we need to calculate angle of asymptotes. And angle of asymptotes is plus or minus 180 degree 2q plus 1 divided by n minus m, where n minus m is nothing but n is number of poles, m is number of zeros. In this problem I have 3 poles, 1 zeros, that 3 minus 1, 3 minus 1 2, then plus or minus 180 degree 2q plus 1. If you put, then we will get plus or minus 90 degree. Because I have 3 poles, I have 1 zeros. Therefore only one root locus branches start from poles and it will end at, that is zeros, s equal to minus 0.485. Maybe these root locus branches start from this pole s equal to minus 10, will go and end at s equal to minus 0.58. These one root locus branches. And also we get the angle of asymptosis 180 degree, plus or minus 90 degree. This is a angle of asymptosis line. Maybe my root locus branches, if it is these poles, it will start from like this. This will comes to like this. These were root locus branches. It will pole, these root locus branches start from poles. It will follow the path of 90 degree asymptotes. It will meet at zeros at infinity. The same way these root locus branches start from these poles. It will follow this minus 90 degree asymptotes. It will meet at zeros at infinity. We try to sketch these root locus in MATLAB, and we see. So basic autopilot system uh, with a landing configuration for inner loop. So where numerator is here 0.585. My denominator is a composite of two functions, that is called as one is elevator transfer s plus 10. Then your aircraft dynamics is s square plus 1.5s plus 1.47. Then your g is equal to 12 times of your transfer function into numerator comma denominator. Then we sketch your that we use r locus command. We will see the root locus branches. these were root locus branches. Okay, so one root locus we need to find out breakaway as well as break-in point also. Okay, so here if you see here this s equal to minus 10 volts, the root locus branches moves along this direction. It will intersect or it will maybe break away path. It will meet at 0 at infinity. Okay, so I'll see here. So these root locus branches will be tell us while varying your rate gyro sensitive value. If you see here in your varying this rate gyro sensitivity, how my closed loop poles of the system will be varying. That we will see in this root locus. So here in this location my gain value is 1.11. I have a damping, my closed loop system having a critical damped system. There is no overshoot. My frequency is 8.919. So now I'll come to here, my gain. So here my gain, it means it is a rate gyro sensitive value. If the rate gyro sensitive value is 2.07, I have a damping is 0.94. That is your overshoot is to be 0.014 percentage. So we keep on moving along this direction. If see here my gain values almost 2.5, 4, 2.48. Okay. My gain value is 2.5. What is my damping? My damping is 0.871. So initially I select my rate gyro sensitive for this basic jet transport aircraft for landing calculation. I select my rate gyro sensitive values is 2.5. At this location my damping is 0.871. So we choose, why we choose a high damping, because this system also having outer loop. So if we choose the damping for inner loop is so high, it will be leads to your close and also it will that outer loop also having some amount of damping. Okay, that's why we select this my rate gyro sensitive values is 2.5. My damping is 0.871. Okay, now we sketch the root locus for your outer loop, then we check your amplifier gain. Okay, so when this rate gyro sensitive value is 2.5, my damping is 0.871. Okay, so in this case we select your rate gyro sensitive for your complex poles, because this location is to your complex pole. The pole is 5.32 plus 2.99 I. My damping is 0.871. Okay. So why we choose your high damping for your inner loop means, suppose that if this you consider your outer loop, that outer loop closed loop is tendency to reduce your damping. That's why we select the gain value for inner loop gain is higher value for a higher damping. Because if you incorporate your outer loop system, see here this is your outer loop system. So So if you incorporate your outer loop system, that will pull this where aircraft to be a lesser damping. So that's why we select for your rate gyro sensitive value as well as high value for your slightly higher damping of your as compared to your inner, as compared to your outer loop. Okay, so now I will sketch the root locus for their inner loop. Then I select my rate gyro sensitive values. The gain value say 2.5. At the time my damping is 0.871. Okay, so the inner loop having higher damping. Why we need inner loop having higher damping means, if you couple with your outer loop, the outer loop closed loop holds tendency to reduce the dampings. So if you initially select the inner loop having lower damping, if you incorporate with your outer loop, it is also reduced to your lower damping value. So if you, the damping is very less, then I have a peak overshoot. That's why we select the gain damping is a higher damping. The respective gain is 2.5. Here damping is almost 0.871. So the outer loop is, if the damping is slightly 0.5 or 0.6, then it is to be a design for good control system. That's why initially we make it, the inner loop damping is 0.871. That my rate gyro sensitive value selected as a 2.5. So now I go to, while sketching the inner root locus, then we select your rate gyro sensitive value. That means here this SRG, then we can as consider as a KRG, rate gyro sensitive values is 2.5. Okay, my damping ratio for inner loop is 0.871. Now we investigate the root locus for your outer loop system. Okay, and what is your outer loop system? Now we close this first. We close this inner loop. So now the inner loop, we select your rate gyro sensitive value say 2.5. So now plus sign, that is where servo amplifier gain. We use, whenever if you use this K is called as your gain value, gain of your amplifier. Then this were inner loop plus minus. Then we combine both these transfer function, aircraft as well as elevator transfer function. That is called as your 12 times of S plus 0.585. Then S plus 10 into S square plus 1.5 plus 1.47. Then from that we get rate, velocity rate feedback, pitch rate feedback. That gyro sensitivity, rate gyro sensitivity value, we found the value say 2.5. For having a higher damping, we choose the damping is 0.877. This one theta dot. If we integrate this, we will get theta. That I push in 1 by S. Then we will get theta. That will be feedback to here. Unity feedback. This is called as one theta. This will theta reference. Okay. Now we these were inner loop. Now we reduce this inner loop. This were inner loop. Okay. You see here inner loop, that is called as your negative feedback control system. It's because the theta dot is a feedback with the minus sign here is a negative feedback control system. So if we consider this, if these whole things if we consider say G of S, then it is a negative feedback plus minus sign, where h of s to be your feedback here. If it is this is a h of s, then the whole transfer function, if you want to reduce this block, then it is called as for g of s, a transfer function, TF, a transfer function, g of s divided by 1 plus g of s into h of s, because it is a negative feedback control system. That's why here we use a plus sign. Therefore, this transfer function for this inner loop, this is your inner loop. Okay, that is what is your g of s. G of s here 12 times of s plus 0.585, s plus 10 into s square plus 1.5s plus 1.47, where h of s to be 2.5. Therefore, we apply this equation 12 s plus 0.585 divide by s plus 10 into s square plus 1.5s plus 1.47. These were g of s divided by 1 plus g of s, again 12 into s plus 0.585 divided by s plus 10 into s square plus 1.5s plus 1.47 into where h of s value, this feedback is 2.5, we multiply with 2.5. Therefore, your transfer function, if you cross multiple, then we common divide s plus 10 to s square 1.5s plus 1.47, both will be cancelled. Therefore, we will get 12 into s plus 0.585 divided by, if we cross multiple this value, then 1 into s plus 10 the whole thing, then we will get s plus 10 into s square plus 1.5s plus 1.47 plus 12 into s plus 0, 12 into 2.5, 12 into 2.5 we will get 30. So we use here 12 into 2.5, just multiple these two values, means 12 into 2.5, that will be get 30 times of s plus 5, s plus 0.58. Okay, that is, then divide by s plus 10 into s square plus 1.4s plus 1.47. This term will be cancelled. Once we cross multiple, then we cancel this term. Therefore, your transfer function for your inner loop, what is your the closed loop transfer function of your inner loop? We remove this entire loop, then we put as your transfer function 12 times s plus 0.585, then divide by s plus 10 into s square plus 1.5s plus 1.47. Again, we simplify this. So what is your transfer function for inner loop? Transfer function is to be 12 times of s plus 0.585 divide by, if you multiple s plus 10 into this s square plus 1.5 s plus 1.47, s into s square will get s cube, then plus 1.5 s square, then plus 1.47 s, then if you multiple 10 we will get 10 s square plus 15 s, 10 s square plus 15 s, then 1.47 into 10 we will get 14.7 plus 14.7, then we multiple inside 30s plus 30s, and plus 30 into 0.585 multiple with 30 into 0.585, we will get 17.55 plus 17.55. Therefore, your transfer function for this inner loop 12 times s plus 0.585 divided by s cube plus 1.5 s square plus here 10 s square then we will get 16.5 s square then here 30s plus 15s 45s plus 1.47, then we will get 46.47s, then here 17.55 plus 14.7 we get 32.25 plus 32.25. Therefore, we remove this inner loop, then we set your transfer function Tf equal to 12 times s plus 0.585 divided by s cube plus 16.5 s square plus 46.47 s plus 32.25. Now, we remove this inner loop, we remove this inner loop. What is the transfer function of their inner loop? S plus 0.585 is whole thing divided by, what is the inner loop transfer function? S cube plus 16.5 s square in 46.47 s and 46.47 s, then plus 32.25. Now it is your outer loop of your jet transport aircraft, yeah, autopilot system. Okay, so here this two block is again multiple, then 1 by s into this whole thing then again we will get 12 into s plus 0.5, 0.585. If you multiple with 1 point s this block, then this s cube term now it will comes to s power 4, then s square term come to s cube, then we multiple with 1 by s, then it will get s power 4, then it is 6.5 s cube, then it is 46.47 s square, then it will be 32.25 s. Now we remove this 1 by s also. Now this is your outer loop. So now we are going to sketch the root locus. Initially we assume your amplifier gain is to be 1 for your outer loop of your autopilot system of your jet transport aircraft. Okay, now they use your, what is your transfer function? So we simply use this command in MATLAB. Your numerator having transfer function is 1, s coefficient is 1, then 0.585, and 1, 0.585. Then your denominator having transfer function, the coefficient s square coefficient is 1, then x cube is 16.5, then 46.47 s square, then 32.5 s. There is no constant term, therefore the coefficient is 0. Now my transfer function, if you consider these whole things g, then your g is equal to 12. 12 is there, therefore 12 times of your transfer function, 12 times of my transfer function tf. I define numerator comma denominator. Now I sketch r locus of my g. I use this command, then we sketch the root locus for your outer loop control system. Go to MATLAB, choose this one, use this. You see here, your numerator having the coefficient is 1, 0.585. My denominator having the coefficient is s power 4 coefficient is 1. Then s cube is, we get 10.5, 1 minute, we get 16.5. Into s square, then 1 we will get 1.5 s square, then we will get s cube plus 16.5 s square. One minute, 46.47, then 32.25 is there. We will get 10.5. What we get here? Multiple s square into s, we will get s cube, then 1.5 s square, and plus 10 s square. We will get 10 s square, then we will get 1.5 s square, and here 1.5 s square, here 10 s square is there, so we will get 11.5 s square. So here, if we multiple, we will get s cube 1.5 s square plus 1.47 s, and 10 s square plus 1.5 s square. then we will get 11.5 s square, not 60. 11 s square. 5 s square plus 46.47 s plus 32. Okay. This will be 11.5. 46.47, then 32.25, that coefficient is constant coefficient 0. Then your transfer function g is equal to 12 times of your transfer function numerator comma denominator. Then we check your root locus. This is a root locus study for your outer loop system. These were root locus branches for the outer loop system. You will see here. This is the outer loop poles. When the gain is 0, that it is having a damping is 0.871. Come along this direction. Yes, we put initially, if you see here, in the previous case, I select my gain value is 2.5. That means the rate guided sensitivity gain is 2.5. My damping is 0.871. 0.871. You see here, my damping is 0.871. Okay, so if initially the gain is 0, that is 0.871. If you increase my gain value, it is tendency to reduce, it will increase likely that it will comes to here. If you look at my gain value is 3.6 or 3.88, go along this direction. If I increase my gain value, suppose my gain is 3.88, that will go leads. Then if you increase your gain value, your damping will be reduces. Okay, these gain values almost 3 point, or if we select 4.7 or 3.8, you see, if we go along this direction, my damping is reduced. So while if you having higher damping as your inner loop, that is tendency to pull this closed loop system to lesser damping. Okay, so if we see, if we increase my rate gyro, so the amplifier gain value, my damping will be reduces. See here, my damping goes 0.226. If I have a gain value is 13.9. Therefore, slightly we need to have a higher damping value. Because if you have a higher damping, then we have lesser overshoot. Therefore, we keep the damping is for all this almost 0.7 or higher than this 0.6. Select 0.72 or 7. 0.769, 0.425, it will become 4.15. This will call this where if the gain is 4.15, my damping is 0.8. Okay, so if we keep on increase your gain value, it is a tendency to this closed loop moves your right hand side of the spec. So where your gain values, if you see here, if you go your gain values is 35.8. If you put your amplifier gain is more than 30.58, the system comes to unstable. See, where when the root locus branches cross the imaginary axis, my maximum gain value of amplifier is to be 35.9. If this 35.9 I have lesser damping. That means that almost the damping is 0. Almost the damping is 0 means the system having 100% overshoot. If it is 100% overshoot, then the system having oscillatory response. Therefore, the system is marginally stable. The system is to be marginally stable. Okay. So, That's why we select your rate gyro sensitive feedback values for a higher damping. If we select higher damping, so if we select the rate gyro sensitive value is this case, my rate gyro sensitive value is 2.5, my damping ratio is 0.871. So if the inner loop is having higher damping, that outer loop, all because the outer loop is outer loop pools, the outer loop of your closed loop pools are tendency to reduce your damping. That's why we are selecting the inner loop having a higher damping. So if we select your damping ratio is 0.871, that rate gyro sensitive value is 2.5. Okay, from that we observation we came to know that there is a essential for rate gyro sensitive. If we select your, if you put the rate gyro sensitive feedback, then I have a higher damping. If you have a higher damping, that will be leads to reduce your overshoot. So I will give to assignment to you. We try to sketch the step response of your inner loop with rate feedback or without feedback. Suppose if you take this for inner feedback, inner loop, in this inner loop without rate gyro sensitive, what is my step response? If I add the rate gyro sensitive, what is my step response? If you go through these two cases, we came to know that what is